Early on in the course, when we first started to examine the motion of real-world objects, we made the simplifying assumption that we would focus on a part of the total motion, the translational motion, which meant that we focused on the average position of the object, which we called the center of mass. Up until now, we have identified the center of mass by eye, often by using symmetry. We'll still do that. However, we'll now discuss a more precise way to find the center of mass of a system. Let's first consider a case where our system can be well described by three distinct point masses and corresponding locations described by position vectors. We're interested in finding the average location, so as a first attempt, we might try to calculate this average in a way that we would probably first try for most anything that we're trying to average. Namely, just add up all the elements, here all the position vectors, and divide by the total number of such positions. You might see that there is a problem with this. If we keep the locations fixed but change the masses, the average wouldn't change. This doesn't seem right. We would intuitively expect that the positions of the big masses should count more in the average than the positions of small masses. So here's a way to fix this. Take the position vector of each point mass and multiply it by the mass, and then add up all these terms, and after that, divide by the total mass. The result is what we call the center of mass. A few things to note here. First, this is an example of an average we call a weighted average. Note here the word weight doesn't mean gravitational force. The word weight here means that some of the quantities in the average count more than others. Here we give more value to the positions of big masses when we are finding the average. Second, the actual physical location of the center of mass is a property of the system, and as such, does not depend on our choice of coordinate system. However, be careful here to note that when we calculate the center of mass, we'll often need to choose a coordinate system. And so, our representation of the center of mass will depend on that choice of coordinate system. For example, here, when we specify locations using position vectors, we have already made a choice of coordinate system origin. So the result of our calculation to find the center of mass will be in terms of that coordinate system. We would be free to choose another choice of origin to represent positions. The representations of those positions would change, and the representation of the center of mass would change. However, as we know, the physical locations of the particles will still be the same, and so too the average position, or the center of mass. Third, the center of mass of a system can lie outside of any piece of mass in the system. The center of mass does not have to be attached to or inside a piece of matter. Fourth, we show here the center of mass defined for three masses. However, this procedure works for any number of point masses. Now, with all this in mind, let's try to calculate the center of mass for this example. Here we show how to do the calculation correctly for this coordinate system choice, where the bigger mass is located at the origin. You can try this with a different coordinate system, say choosing the origin to be at the location of the smaller mass. The component representation will change. However, you'll find that the actual physical location of the center of mass will still be the same. This approach to computing the center of mass will work even if the pieces of mass in our system are large. As long as we are able by some means, say by using symmetry, to find the center of mass for each piece, then we can use the same averaging procedure to find the center of mass of a collection of large objects. One final point to make before we end this lecture. Even in the case where we have a system that is made up of continuous objects with no obvious symmetry, we can still find the center of mass by generalizing this procedure. We divide up the object into a large collection of small pieces we can treat as point masses of mass delta m sub I. We multiply the position vector r sub I of each piece by its mass, and add up all the pieces and divide by the total mass. In the limit that the delta m sub i's become differential elements of mass dm, the sum becomes an integral. Physically, we're still doing the same thing, a weighted average performed by summing up the positions of each piece weighted by its mass and dividing the total sum by the total mass. We won't spend time doing these types of integrals here, but it's important that we at least have in mind the concept of how to find the center of mass even in these cases.